So this is our second experiment. So in this experiment, the title of the experiment is shear force and bending moment diagrams of a beam. So we have a overhanging beam here, and he has given the span of the beam as 10 meters, and it is subjected to a UDL and a point load. So here you have a UDL from A to B. It is a UDL of magnitude 10 kilonewton per meter, and a point load of 20 kilonewtons is applied at the free end of the overhang. Then for this beam, we need to draw the shear force bending moment diagram. And also the cross section of the beam, he has given it as a I section is the cross section for that, and the dimensions for the cross section is also given in the picture. So from this we can identify what are the details of cross section of this beam. So now for this beam, we need to draw this. This is the analytical solution. You can see that this is the shear force diagram and this is the bending moment diagram. So now we need to plot the shear force diagram and bending moment diagram using software, and we need to compare that with respect to this. So then whether we are getting the same values, especially what we need to look at it is what is the maximum positive shear force and what is the maximum negative shear force. Similarly, what is maximum bending moment and what is the maximum negative bending moment. But here, maybe people will follow different conventions for shear force and bending moment, because some people will follow to the left of the section upward is positive, some people will follow the negative. So this picture I have taken from the internet. So whatever he followed is upward to the right or left of the section, upward force he has taken it as positive. But in the software, we'll get it reverse. So don't bother about that. You need to look at only, suppose if I take location A, what is the magnitude of the shear force? I need to take that is 25. So here similarly at point B, it is 15. Point C, it is 15. Point D, it is 20. So point C here on the positive side, it is 20. That means total is 35. So first we need to look at these magnitudes. So because the sign convention is different from people to people, person to person. So first I look at the magnitude and then I look at the shape, whether it is varying linearly or whether it is constant. So then if those two matches, then it's okay. It's okay for me. Whether it is negative or positive, I don't matter. But only thing is while writing the results, we need to write a maximum positive, maximum negative means whatever you get from the software, you follow that sign convention and write it accordingly. A similar thing you can follow for the bending moment diagram also. Maybe some people will take this hogging bending moment as positive, sagging as negative. So other people will take in a reverse way also. So maybe whatever shown here in this picture, so whatever solution we got in the simulation, that is in the answer is the sign convention wise it is opposite. So that means here, okay, bending moment you will get the same thing, something like this only, but shear force you are going to get in opposite direction. You keep that point in your mind. So just in case of shear force, just check the sign and how it is varying. For bending moment, as you are going to get something like this only. So for that, what you have to do is, so you need to see the shape of the curve. Here it is something like a parabolic curve, and then you have a straight lines. So you need to see that, and also you need to look at the maximum values. If the maximum values are not exactly same, then you need to compute what is the percentage of error. So this is the actual problem for us. So we have given a overhanging beam. So that overhanging beam is subjected to here 10 kilonewtons and 20 kilonewtons load, and he specify the distance between the supports as 8 meters, and he has given everything in the diagram. If you look at the diagram, it will be self-explanatory. You can understand everything about the configuration of the beam and the loading conditions and support. So but here once you have done this, so actually to draw the shear force bending moment diagram, you don't require any Young's modulus or you don't require any Young's modulus here. So only require okay. So but you don't require anything here. So only with the loading diagram you can solve for shear force and bending moment diagram. But in the software, so it is designed such that whatever analysis you do it, the material property you need to input as must. So you need to give material properties. Without material properties, it won't solve the problem. Even though in this problem you don't require material properties, well, so you want to solve this problem also in the software, you need to give some material properties. So that's why here the beam is, we are assuming beam is made of a mild steel with a modulus of velocity as 200 GPa. So we'll assume that Young's modulus, even though it is not going to influence your solution, but see in the software it will not only calculate the shear force bending moment, it will calculate the deflections and stresses also if you solve the problem. So that's why to compute the deflections it required Young's modulus as well as the cross-sectional details. So for that matter, simply to draw the shear force bending moment diagram, you don't require cross-section also. But still, we need to input the cross-section. Then only it will solve for you. Otherwise, it won't solve. It will say that there are no materials are defined for our model. Like that, it will give a error or warning or error, whatever it may be. So therefore, even though the material properties and cross-sectional details are not required, we need to define them in the software. So then only it will solve. Why are required is generally, I think you may have familiarity with your FEM. So if you want to solve any problem through the FEM, you need to construct the stiffness matrix and load vectors if it is a static problem. To construct the stiffness matrix, you require, if it is a bar, A, E, L. If it is a beam, you require I, E and L. So L is given through this geometry, but moment of inertia, area moment of inertia, you can define that through only cross section. That's why you need to define I. And of course, you need to input the E value also so that it can compute the stiffness matrices. So then once it is calculated the stiffness matrix, it will calculate all the required things. So then it will construct the stiffness matrix for every element and then it will assemble all those stiffness matrices. Once you done that, so if you apply the load conditions based on that, it will apply either a penalty approach. Here the software will use penalty approach. Instead of elimination approach, it will use penalty approach. So to solve for to introduce that boundary conditions, then it will write the equilibrium equations as K into U is equal to F. So you can solve for, the software can solve that using some iterative techniques, then it will give you the solution. So only here takeaway point is, even though it is not required, material properties are not required, so you need to input those material properties and cross-section details in the problem. Okay, so this is the problem description. Then how I can model this one in the software. So the name itself suggests that it is a beam. So here the structure is a beam. That means whatever element we have taken earlier problem, first experiment, that is a bar problem, axial load problem. If you read that element description, that element can support only axial loads. But here you have a transverse loads. So that means you cannot take same element for this one also. So now we need to take another element or separate element for this analysis. And that element, what we are going to use, it is beam 188. So in this case, again, this beam 188 also will have two nodes. And each node it has 6 degrees of freedom. Earlier element, you have only each node have 3 degrees of freedom and there are only 3 translations. Whereas in case of beam, you have 3 translations. In addition to those 3 translations, you have 3 rotations also. So in case of bending, you require rotation. That is why we can't use the earlier element because that doesn't have any rotational degrees of freedom. So here this beam will have 3 degrees of freedom. So 6 degrees of freedom for each node. So in addition to those 3 translations, it have 3 rotations also. So now once I select the element, then I will define the material properties and then I can define the section properties. So that I will show you how to do in the software. So once you done that, then what you need to do is you need to identify how many number of elements you need to consider for your analysis. So here, let us say initially we assume that in the model we are considering 200 elements. So again here the number of elements will depends upon the user choice here. If you take less number of elements, your solution accuracy will be less. Or else computational time is small. So that means if with less number, you can solve this same problem with 2 elements or 3 elements or 4 elements, like that, whatever elements you can take it. But if you take 4 elements, whatever solution you got it, that is going to be less accurate. So that means here you have analytical solution. If I compare the results of that 4 element model with this, there is a lot of percentage of error. So therefore, what we need to do is we need to take an optimum element size such that it can solve in a minimum time, and at the same time the solution accuracy should be sufficient. So that means whatever results you got, those results should be within the acceptable level. That means the percentage of error, if you compare the solution what you get from the software, and if you compare that one to with respect to this analytical solution, so the percentage error should be at least, it should be less than 5%. Then only we can say it is a acceptable solution. So for that, so first I tested, I choose a 200 elements. So that means I need to divide this entire beam into 200 elements. So here in the previous class, whatever we discussed, so there are two types of approaches to create an FE model. One is direct approach, another one is indirect approach. In case of direct approach, you can create nodes and elements directly. So because in the previous problem you have only 2 elements and 3 nodes, I use the direct approach. But here in this particular model, I want to create 200 elements with 201 nodes. So therefore 201 nodes, manually creating 201 nodes means input what are the coordinates for all those 201 nodes. Then you need to create these 200 elements. So it is going to be a tedious process. So therefore what I'll do is, instead of creating the directly nodes and elements, first I'll create the geometry, then I'll convert the geometry into FE mesh using a meshing option is there in the software, mesh tool, we'll call it as. Using that mesh tool, I'll convert the geometry into FE model. So once I've done that, then you need to apply the support conditions. So supports are, you need to apply the supports, and also you need to apply the loads. Then I need to solve for it. So that is the only thing we need to do it. So now if you look at that, this is a UDL and this is a point load. Software has a provision of applying UDL as a point load. Of course, suppose sometime you may have pending movement also. Movement will also apply some other points. In this problem, it is not there. So if you want a movement also, you can apply movement also. And not only UDL, you can apply UEL also. Something like a trapezoidal load or triangular load is there. So that is uniformly varying load. So you can take uniformly varying load also. Software can provide you with that option also. So only, but here we have only UDL and point loads. So, and coming to the boundary conditions here, these two are simple supports. So now if I talk about the boundary conditions here, see our entire beam is in a plane. So that means it is a two-dimensional structure. So it is going to bend in only XY plane. You can see the here coordinate axis here seen, X is this and Y is like this. So it is going to bend in only XY plane. So that means the load is applied in XY plane only. So that means other direction we don't require. Even though if you look at the element description here, it has 3 translations and 3 rotations. So here I required only, my requirement is only horizontal displacement and vertical displacement and rotation about Z. Only 3 degrees of freedom are sufficient for me to solve this problem. But the software, all the elements are designed for the general purpose. So I'll use that general purpose. Whatever element degrees of freedom is not required, I'll constrain them. So now here this end is simply supported, means here the constraint, what are the constraints I need to apply is, I need to apply the translation along X, along Y should be constrained, and at the same time the rotation X and rotation Y are constrained here. Similarly, if I take this support at C, point C, here it is only a roller support. So in case of roller support, only the vertical displacement is constrained. So that means I need to arrest UY, and in addition to UY, rotation X and rotation Y are not required. I need to apply those two also. So that's it. So I'll apply these constraints, I'll apply these loads, and then I'll solve it. So again, like in the first experiment, we need to use here also element table to draw the shear force bending moment diagram. So before that, you need to compute support reactions also. So that directly you will get from the general post processor, you will get the support reactions also. Okay, so this is the explanation about how you can solve the problem in the software. So now I'll go to the software. So then we'll see how we can solve this problem in the software also. I'll open the software. So in the previous class, I already told you everything, how to set up your working directory and how to save the files, all those things. I already told that. So now I'm not going to that because I want to close this class as early as possible. Time is given to me only 1 hour. So I have to complete within the 1 hour. So that's why I'm not repeating all those things, whatever we discussed earlier. So straight away, we move to the problem. So first, we need to choose our element, so which is nothing but I can go add and edit. So we need to select a beam element. In that we have two types of elements are available to you, 2-node element or 3-node element. So first we'll select it as 2-node element only. So now it is getting added here. Close it. Then I'll define the material properties. So this is also already known to us. So I need to define the structural properties. So in this, now Ex you need to define. So what is the value of Ex is given in the problem? He has given it as 200 GPa. So, but here, if you look at the loading conditions there, the load is in kilonewtons. So therefore, always like I mentioned in the previous class, your load unit should be consistent. If the load is in kilonewtons, so Young's modulus also I need to give it into kilonewton per meter square. So length unit again we are taking it as a meter. So therefore I need to define E as 2 in terms of kilonewton per meter square. So therefore whatever load he has given, that is 200 GPa, Young's modulus is there. Here what is the Young's modulus he has given? 200 GPa is there. So I want to convert this one into kilonewtons. That means if I convert this one into kilonewtons, what I am going to get is kilonewton per meter square. We know 1 Pascal is 1 Newton per meter square. GPa means 10 power 9. So 200 into 10 power 9 Newton per meter square. But I want kilonewton per meter square. Then I can write it as 200 into 10 power 6 kilonewton per meter square. So therefore here, while inputting the data value here, what I need to do is I need to give 200 10 power 6. So 200 E6 I can give it as. So nothing is given about Poisson's ratio. I'll take it as, since it is a one-dimensional problem only, I'll take Poisson's ratio as 0. Then enter. So that's it. So that is the only material properties required. So apart from that, you need to define the section properties also. So like I mentioned, even though that these are not required to solve this particular problem, but still we need to input it. So to define the sections, I'll go for the sections here. Then in that beam, common sections, you need to click on the common sections. So then you have a subtype is there. If you want, you can name something. If you want to name it I section or something, whatever name you want, you can give it name here. So I'll say beam section. I'll give the beam section as a name. So then you can select here type of the section, whatever you want here. So different types of sections are available here, but for us, he has given it as I. So I selected I. See then, if once I selected I here in this box subtype, so the shape is visible here, and also it is given the different parameters for that section, and those parameters are given here. So you need to enter these values here in this box so that it can calculate the properties for that section. So now if I go to that one again, see here what is required is W1. So that means the flange width. You need to require bottom flange width. W2 is the top flange width, and W3 is the total height of the section. And you need to input what is T1, what is T2, what is T3. So in the diagram, he has given all those properties. So T1 is nothing but T1, T2 are the flange thicknesses, and T3 is the web thickness. So with that, in the diagram, he has given everything, all those properties. But only thing is, here he has given in mm, but we are solving the problem in meters. So therefore, you need to convert this one into meters. So now if I take a flange width, so both are same. Here W1 and W2 both are same. 120 plus 6 plus 120. That is 246. So 246 mm. So I need to convert that into meters. So if I convert that into meters, so here W1 is equal to 0.246. I need to 246 mm is there actually. So I need to convert the 246 mm into meters. So I'll give it as 0.246. Even your W2 also same, 0.246 only. Then height of the beam is given as, go to that again. Here the height is 600 plus 8 and plus 8. 600 plus 6 is 16. That is 616. So then again you need to convert that one is also into meters. So it is 0.616. 0.616. Then T1 and T2 he has given place thicknesses that he has given it as 8. 8 means 8e minus 3. I can write it as 8 mm is given. So I need to convert that one into meter. So therefore it is 8e minus 3. And this T3 has given it as 6 mm. So I need to enter it as 6e minus 3. So once I enter it, simply if I click on apply, so then it will get. So now if I want to see what are the properties of that section, simply I can click here on the preview. See now if I click the preview here, you can see showing the section I section here, something like this, and it is calculating the centroid and shear center for the section. Of course, it is a symmetrical section symmetrical about both the sections. Your shear center and centroid both are coinciding with each other here. So here on the right side, you can see the section summary also. Area, IYY, IYZ, IZZ, it is calculating all those properties. So that means the section property, it is taken in a YZ plane. So the length is X direction, and YZ section properties are taken in the YZ plane. So now you can verify these properties also. Okay. So anyway, so we are not going to give much importance for this, because in our problem these properties are not going to influence our solution. So just we'll check whether that it is taken or not. So that is sufficient for us. Okay. So then once I done that, so first I selected the element type, then I define the material properties, then I define the section. Next I want to move, I'll move to create the geometry. So geometry is nothing but here I need to create this line. So to create this line, what I do is wherever points he has mentioned, that is salient points A, B, C, D. So for AB, I'll create one line. For BC, I'll create one more line. And for CD, I'll create one more line. So that means total I need to create 3 lines. So we know to create a line, you require starting point and ending point. That means you need to create one.
Hello. Hello.
Hello.
What man, Ashok?
ఎలా బుద్ధి
రికార్డ్ అవుతుంది.
I know, man.
హలో
Sir, your voice not audible, sir. Sundar, sir.
సార్ లేరు. 14.
సార్ లీవ్ అయిపోయారు.
Sir, Abhinav, sir, class చెప్పండి, sir.
మీరున్నారు, మీరు చెప్పండి.
రికార్డ్ అవుతుంది పృథ్వీ.
I know, man.
బ్రో ఎవరైనా ట్రై చేస్తున్నారు ఇప్పుడు సాఫ్ట్వేర్ లో? చేస్తున్నా వస్తుంది ఒకసారి.
సార్ కాల్ చేయండి ఎవరో ఒకసారి.
సిఆర్ సుందర్ చేస్తాడు.
అన్నీ క్లీన్ చేయరా?
Okay. So, okay, I think now I am audible, right?
Yes, sir.
Okay, maybe meantime there is some connection with the internet. So I don't know at what time it is disconnected. So just I think I explained about how to take these elements, all these things. So at what time it is disconnected?
After I section definition, sir. Defining I section.
Define I section for the in the software, right?
Yes, sir.
Okay, right. So okay, I'll take you back to that. So now I'll go to the sections. So I'll tell you how to define the section now. Yeah. So
The screen is not shared, sir.
huh?
The screen is
Screen
not
not
visible,
visible.
sir.
Huh? It is not visible. Okay. I'll share it. Okay, I think now it is visible, right?
Yes, sir.
Okay. So here, first we define the section just by specifying W1, W2, W3, T1, T2, T3. So if you look at the diagram, what he has given in the problem, here, so this one is W1, width of this plane is W1 and top planes and bottom planes both are same. Here it is 120 plus 120 plus 6, 246, but we need the input that one as in meters, so that is 0.246. Similarly, height is 600 plus 8 plus 8, 616, so that we need to give it as in meters again, that is 0.616, and plane thicknesses is, he has given it as 8 mm, so top 8 and bottom is also 8, so we need to input that one as also in meters. Web thickness is also 6 mm, so that also he has given it as 6 mm, that also we need to give it in meters. So now I define the properties accordingly here in the section. You can see that W1 and W2 same, which are 0.246, and W3 is 0.616, and thickness of the planes T1 and T2 are 80 minus 3, that is nothing but 0.008 meters, and thickness of web is 0.006. So once you've done that, so then just you can see, if you want to see the section properties here, you can see that here, if you click on preview, it is showing the section for you. So in the entire section here, you can see that it is calculating centroid as well as shear center. Of course, this is a symmetrical section. It is coinciding with centroid and shear center is coinciding with each other. And on the right of the section, you can see the properties also. What is the area? What is the moment of inertia? IYY, IYZ, IZZ, like that. That means here it is calculating IYY, IZZ, IYZ means your section is in YZ plane and your length direction is X. Okay. So this is how, but anyway, so these properties are not required for us. Just we are seeing whether it is done, it is taken properly or not. That is the only thing. So for the verification only we are doing that. Okay. Right. So once you've done this, then next what I'll do is I'll go for creation of the geometry. So to create the geometry, what you have to do is, see here your beam is having three spans, A to B, B to C, and C to D. So now I need to create these three spans by three lines. So that means I have to create a for span AB one line, for span BC another line, for span CD another line. So, but to create the lines, I require a key points also. That means vertex points. So that means the starting and ending point I required for the line. So therefore, for that, what I need to do is I need to create the key points at A, B, C, D. So for that, I will assign the coordinate system at one location. So let us take that. We'll assume the coordinate system origin is at point A. So in that case, the coordinates of point A is 0, 0, 0. Only we'll talk about x coordinate. Y and Z are obviously 0. So at A it is 0, at B it is 4 meters, at C it is 8 meters, at D is 10 meters. So total 10 meters, length is 10 meters. So D I'll get 10 meters, x coordinate is 10 meters. So now I'll do that in the software here. So maybe I already done that. So before connecting off here, see I can show that also. Plot key points. Okay, so I created like this. Anyway, I'll do that again. So anyway, first what I'll do is I'll delete these things and I'll do that. So I'll go for modeling. Then to delete that, what I need to do is I need to go for I created lines also. Then what I'll do is I'll delete everything. I'll select all these lines and I'll create everything. So now if I list the key points, now if I go for listing, see it is saying that no key points to the list. Now that means there is nothing is there now. I'll start it again scratch. So key points, first I'll go for create key points in active coordinate system. So here I'll give first key point and that is at point A, its x coordinate is 0. I'll apply. Then I'll go for second key point and whose x coordinate is 4. I'll enter 4 here, apply. Then third key point, then whose x coordinate is 8. I'll apply. I'll click apply. I'll check whether it is not created. Apply. Then the last one, fourth key point is at 10 meters. So it is 10 here. Okay. So like this, I created the key points. Now using these key points, I need to create the lines. So for that, I'll go for lines. Then I'll use straight line option. Then I'll join 1 and 2. That is the first span A and B. Then 2 to 3. Then 3 to 4. Then click OK. So that means this is my geometry of the beam. Now in the geometry, I don't have any elements now. If you can see that here, I don't. If I plot it, I can have a coordinates key points now. See, you can see that we have 4 key points, and similarly you have 3 lines also here. 1, 2, 3. You can list those things also. List loads, not loads, lines. Okay, like this. You can see that. You can see it is saying that you have 3 lines: number 1, number 2, and number 3. So if you want to check which one is line 1, which one is line 2, like that also, you can go for here. Go for numbering. In that numbering, you see here you have a line numbers are there. You can keep this on. Even if you want to keep key points also, it will show the key points also. Then you go for plot multi-plots. See now it is L1, it is L2, and this is L3. So line 1, line 2, line 3. Similarly, 1, 2, 3, 4 are key point numbers. So now once I know that, so I don't want this numbering, so that it will be sometimes it is going to be confusing which one is what. So I'll remove it, the numbering. So now I have key points, but if I list the nodes here, what happens? See, it is saying that there are no nodes. So that means I created only lines, geometry. I created only the geometry, but I not created a FE model. So therefore, to convert the geometry into FE model, now what I need to do is I need to go for the meshing. In that meshing, we need to select the mesh tool. So now here to mesh, here this mesh tool will consist of 2 sections here. The first section will call, you can see here it is a size control section. So that means here you can specify the element size here. So element size, or you can specify the number of elements. Anyway, both are same. Either you can specify the size or you can specify the number of elements. So element divisions, that is nothing but again size only. And the second portion here is a mesh tool. So that means using the second portion you can convert the geometry into FE model. First portion is to specify how many number of elements you require, and the second one to specify to convert the geometry into FE model. So now coming to this our problem, we already initially we are taken that we should have 200 elements in the model. So entire line, so this 10-meter span I need to divide into 200 elements. So that means what is the length of each element? 10 by 200, right? So what is the 10 by 200? 0.05. So if I divide 10 by 200, so that means I have a span of 10 meters. I wanted to have 200 elements across the span so that I can get the in order to get the 200 elements, I need to divide the 10 meters by 200 number of divisions. So that I can divide here. See here, I have a lines. So I'll click on set here. Then it is asking for, so you select the lines for which you want to define the size controls. I'll select all the 3 lines, then click OK. Then it is asking for edge length. So here edge length I am taking it as 0.05. If I take 0.05, then only I have 200 elements in my model. So now you can see it here, it is divided now. But still, even though it is showing only size controls, so that means it is showing the divisions means it is not meshed. If you go for list nodes again, what it will say that there are no nodes into the list. That means simply specifying the size control doesn't mean that you converted that geometry into FE model. You need to use the second portion of this mesh tool also. You need to click mesh, then you need to select these lines again so that now your line will be converted into FE model. Now you can see if I go for here list nodes, now you can see here, if I list it now, you can see that now you have a nodes. So if I want to see how many number of nodes there are there in my model, if I go down, come to this, I have 201 nodes. So that's what I have written in that description, element FE model description. We have 201 nodes and 200 elements. Similarly, I can list the elements also here. I'll go for list elements. So now you can see, come down, you can see the number of elements, you have 200 elements. Right? So that means now my model is converted into FE model. So geometric model is converted into FE model. Then what we need to do is, for this we need to apply the loads and boundary conditions. So for that what we need to do is, for simplicity what I'll do is, first I'll plot the lines now so that I can clearly see that where are the spans are there. Because we have one support at this location, another support is at this location, and one point load is here, and UDL is for the first span. So therefore if I plot the lines, it is easy for me selection process. So that's why I'll plot the lines. Then I'll go for the application of loads and boundary conditions. Define loads. I'll go for first I'll apply the structural boundary condition, that is constraints. So structural, displacement, on nodes or on key points also you can do it. So for anything you can apply, no issue. So we know key points, I'll apply for the key point here. So I have a key point here. I'll select first that. So like I already mentioned, we need to constrain UX, UY, UZ and rotation X, rotation Y, because we required only at this node, at this key point or at this node, we required only rotation Z because it is hinged support. So I'll click apply. Then at this support, then the second support, that is at point C, I'll select this key point, I'll click OK. But at that support, UX is not constrained. It is a roller support. So I have to select UY, UZ, rotation X, rotation Y. Click OK. So now you can see that here it is putting the constraints to this key points and this at the 2 locations or at the 2 supports. Then this key point constraints is transferred to the node corresponding to that key point. Then I'll apply the loads. So for that we have 2 types of load. One is a point load, another one is a UDL. So point load I can apply for, see here in the point load option I can apply for the key point or I can apply for the nodes. So that means here I have a node and key point, both are there. I can use any one of these 2 options. So let us say I'll take the option of key point, then I'll select the key point here, I'll click OK. So now our load is in the Y direction. So we need to take it as FY component. Then the load is minus 20 kilonewtons. Why I am taking minus? Because the load is acting in the vertically downward direction. So I'll take it as minus 20. See now it is putting that load here. So then I need to apply that UDL. So to apply the UDL, what I'll save it here meantime. Sometimes, it is crashed. Okay, anyway, so the software is crashed. We need to solve it from scratch again because I not solved it. So I'll quickly do that. So whatever process, you can see that again also then, no issue. So element type, theme we need to select. Then material properties we need to define, material models. So you need to give it as 2e6, then Poisson ratio as 0. Then I need to define the sections, go for beam section. Then you select as I section as your beam section. Then you give the values 0.246, 0.246, 0.616, 0.008, 0.008, 0.006. Then click apply, I'll call it as OK. Then I'll go for modeling. I'll create key points in active coordinate system. First one is at 0, 0. I'll give the auto number now. So then 4, apply. Then 8, apply. Then 10. Okay. Then I'll create the lines. Side line. 1, 2, 2, 2, 3. Okay. So it doesn't matter in which order you create it. Then, okay, let me save it. Then I'll go for meshing, mesh tool. Then under size control, then I need to pick all. I need to give element edge length as 0.05. Then I need to mesh it. So pick all or select all the three. Click OK. So now you convert it into meshing. Then I'll save again. Then you need to apply the loads and boundary conditions. Define loads, apply structural displacement on key points. So for that I'll draw the plot lines. Then I'll select the key point here. Click OK. Then UX, UY, UZ, rotation X, rotation Y you need to select. Click OK. Then here at this location also you have roller support. So you select the key point here. Select OK. So now you need to unselect UX here. So then click OK. Then we'll go to the loads. That is, first we'll apply the point load. That also will apply to the key point. So here I have a key point. So whose magnitude is, you have to select here Fy and its value is -20. Click OK. So now it is done. So then we need to apply the UDL here. So UDL you cannot apply for the lines here. So only the option we have here in the software is you need to go for pressure. UDL is nothing but a pressure. You have to use this option on beams. So now here you can apply this one for only elements. So that means so far we selected only key points. So now here I have to select the elements from this point to this point wherever your EDL. So for the entire span you have a EDL. So therefore to select all the elements instead of single pick here, I'll use this box option. Then I'll draw the box so that it can select all the elements. So something like this. So I need to select all the elements. Then click OK here. So now here load key. So since it is in the vertical direction, I need to give the load key as 2. And since it is a pressure, no need to give it as a negative value because only I need to enter the magnitude. That is 10 kilonewtons. He has given 10 kilonewton per meter. I'll give it as 10. Click OK. So now you can see it is applied. That UDL is applied here for the beam. So this is how you can apply the loads. So now I think this is done. So next step what we need to do is we define everything now. We need to go for the solution. So go for solution, solve, then click on current LS. No need to set anything in the solution controls also. Simply whatever default setting is there, we'll take those default settings and it will solve very quickly also. Okay, it is done. So once your solution is done, then if you go for the results here in our document, so what we need to do is first thing is support reactions. So here support reactions you need to calculate what is the reaction at the left support, what is the reaction at the support, right support. Similarly, next is shear force diagram. Then after that you have a bending moment diagram. So these are the results we need to get from the software. First, if I want to see the reaction solution, for that what I need to do is I'll go for general post processor risk results. Then I'll see that here you can see reaction solution is there. So you can select all items, or I want only a reaction at the y direction. You can see that here your reaction forces are something like this: 24.748 at a left support and 34.752 at the right support. You can see that also. We want to know where it is left, what is node 1 and what is node 2, node 82. You can see that also here where it is located also. Go for nodes and you just select the coordinates, then click OK. See, node 1 is at 0, x coordinate is 0 means that is the left support, and node 82, if you go for node 82 here, see here 82 is at x coordinate of 8 meters, that means at point C. So that means at C the reaction is 34.752 kilonewtons, and at A it is 24.748. So we need to note down these values. So both are positive means the load reaction is in the upward direction. That is also true from the diagram. You can see that it is also true here. So from the shear force diagram, actually here it is 25 and here it is 35. See, we have selected 200 elements. Even with the 200 elements also we are not getting the exact solution. So we are getting 24 point something, but here it is exact value is 25 and 35. We are not getting even 35 also here. So that's why you need to go for more number of elements for your solution. Okay, so first step is that. So I can extract the reaction solution like that. Then to define or to draw the shear force and bending moment diagram, again what we need to do is we need to define the element table. So I need to go for define element table and I need to click add here. So here while drawing the shear force and bending moment diagram, we need to define what is the shear force at the starting of the element. That means that since our element has two nodes, node 1 we'll call it as I, node 2 I'll call it as J. So that means we need to define what is the shear force at first element, what is the shear force at the second first node and second node, I and J. So therefore for first node I'll give the label as SFI. So then I need to use the sequence number. Then what I have to do is I have to use this one here, SMIC. Then what you can do is, okay, so I'll show you the document first, then we'll see that. So what are the numbers you need to follow, all those things. So if you go through the help document, like what I already told earlier case also, then you can open the help document and you can see what are the sequence numbers you required for defining shear forces and bending moments. So I know, but still I'll show you how you can get it. So if you don't know that, or if you forget those values, how you can check those things from the element documentation. So let us wait, it is taking some time to open. Okay, so now here you type beam 188 and click on the search box or just enter. So now you can see that you are getting all the results in the search bar about beam 188. I'll click this first one only. So in that, if I go down, completely output data. See here, you need to look at element output data. In that, you need to see these things, element output definitions. So this table is important for us. So in that, say section shear forces, so SF Y comma Z. So SF Y comma Z is there. So whether it is available or not, here you can see that if result is available, so you can say yes, yes. If it is not available, you can say here you have some other options are there. So here anyway for this element, these results are available. So now I want to see what are the sequence numbers I need to use to extract the shear force and bending moment values. So if I go down further, right, see here you can see here bending moment. So because the moment is about z axis, I need to go for mz. So then item number I have to choose is SMI SC, and 3 comma 16 I need to use. At I have to use 3, at j I need to use 16. Similarly, shear force y I required. At shear force y, again the label item is SMIC, and at I it is 6, at j it is 19. So first we will define the shear force. That means at I you need to use 6 and at j you need to use 19. So now I'll come here, I'll click add. Then first I'll define shear force at I, SFI. I'll give the label as I. Then sequence number, then SMIC, and what is the number here we are seeing for the shear force? So for shear force Y, it is 6 at I. So I need to enter here 6. 6. Then apply. Then I'll take SFJ. Now at J, node J, I need to go for again completely bottom here. I need to select sequence number. Then what is the number for now J for shear force? You can see it is 19. So I need to enter 19 here. 19. Then apply. See now once I click apply, automatically it is get it added here. You can see that. So then I'll go for bending moment at I, BMI. Then again go for sequence number. Then select SMIC. Then what is its number here now for bending moment about Z axis? MZ. So 3 and 16. At I it is 3, at J it is 16. So I need to enter here first 3, then apply. Then I give the label as BMJ now. And sequence number, again here it is 16, right? 16 or 6? What is the value? 16, right? So 16 you need to enter, click OK. Okay, now they are done here. They added here, so that means it is there. So now to plot that, once I define the element table, then I'll go for the plotting that shear force and bending moment diagrams. To plot that, I need to go for plot results. Then contour plots, line element results I need to select. So in that, first I want to plot the shear force diagram. So then here I need to select SFI and SFJ. So I have to select I and J, then click OK. See now this is going to be your shear force diagram. So now you compare your diagram with the whatever given here. So like I already told you, here I'll minimize, I'll keep them side by side so that you can compare it better. See, only thing is the sign convention here it is opposite for the shear force diagram. You can see that also. I'll minimize this also. Oh. Okay, I'll compress them. Okay. Now you can see that. Now you can see you are getting the shape is same, but only thing is you are getting shear force diagram like this. Okay, why you are getting here? This one is in the something like this. There is something wrong in the shear force diagram. Okay, I'll open the software. I'll check whether I given the loads properly or not. List nodes, loads, forces, and all nodes are on all key points. Okay, 20 kilonewtons only. So that is 20 kilonewtons only. We are given properly only. 20, 10. Okay, it is correct only. So, but why it is showing negative direction? Okay, so and if you look at the values here, here you are getting only minus 24.49, means approximately it is 24.5. But if you compare with our actual solution here, it is 25. See, there is some error. You are not getting the accurate value or exact value. So therefore, you can modify the, that means that error is there. So you compute the error between these two. So that is what he has given in the table also. If you go for the result table here, for shear force maximum SF and negative SF, just take the value. So for ANSYS, you are getting 24.5. analytical solution 25, we calculate the percentage of error. So if it is less than 5, okay, you can accept your solution accuracy. Suppose if it is not less than 5, if it is more than 5, then what you have to do is you need to increase the number of elements in your solution and then you need to solve it again. Similarly here, this red color, the max value here, it should be 15. We are getting it as only 14.75. So this red color, so that is also somewhat deviating. And this one is, actually this one should be 20, but we are getting 20.13. So that is also, it is also deviating something from the actual value. So like that, you can take the minimum and maximum values and compare the percentage error also. Compare the analytical and answers, and then you can get the percentage error also. So, and also make sure that the percentage error should be less than your 5%. So similarly, I can go for plotting the bending moment diagram also. So now this is your bending moment diagram. Here you can see that the maximum negative bending moment is minus 39.5, maximum positive bending moment is 39.63. But if you look at our actual analytical solution, here it is 40, here it is 31.25. So that is, okay, you can see that our diagram here. So here it is the maximum. So this red color is, I think around you are getting it as 39. So that means, okay, the 39 comes here. So this is the red he is taking, it is 39, this red. But this color, it is around 30 only. So if you see this color, here it is 30 only. So then you mark those values. So this is 40. 39.5. So you have to get 40. Anyway, you are getting it is 39.5 means it is somewhat close. And the shape is also similar here. Whatever you can see it here in our analytical solution. So this is also similar to in the answers also you got the same. Only in shear force diagram, because of a different sign convention what he has followed, you have a different solution. So now what you have to do is you need to take the picture of these things. So for that what you can do is you can go for your plot controls. Then click here, hard copy, so to file. So here, since the background is black, I want to change the background to white background. So for that, I need to use here reverse video. Then whatever you want here, so whatever format, whether it is in bitmap or JPEG or PNG, you can select your format, then click apply. So automatically, or OK, click OK. So automatically that file will be saved into your working directory. So here I am using D and analysis lab as my working directory. So if I open that, I can see that file is there in that directory. So D analysis lab. So in that you can see that image. So if I modify it, so now see here I saved it 3 times. So you can see that you get that image, whatever image is there in that. See that shear force diagram is coming to me with the black background. So now you take this as image and you need to put that into your record. So in the record, whatever I given there, so I given some space. So in the result section, so what you do is, first after calculating this, below the shear force diagram, you need to enter the values, then you need to put that shear force diagram. Similarly, for bending moment diagram also, you need to enter the values and you need to put the diagram here. So then you can write a discussion about those results. So right, so this is how you can solve the problem. So I think I reached the target within the 10:15. I want to close this. Now it is 10:15. Okay, I'm able to complete the class. Even though there is a little bit of technical glitch, we are able to do that. So now, so this is what I want to explain. So now if you have any doubt or any queries, then you can ask, so that we can discuss, or else we can close it, so that you can attend the next class.
Sir, recorded video link is sir.
Sorry?
Recorded video is sir.
I didn't get what you are asking. Come again?
Will you share the recorded video,
It
sir?
is recorded. No, it is not possible to share, because as per the college norms, we don't want to share. We don't have a permission to share the recorded videos, all these things. If you want to see the video again, so what the HOD is told us is, you come to the class, and then if you come to the college, so then you can see whatever want, you can see. You meet the consult faculty, then you can see the video in the college itself, but it is not going to share in the, actually it is not shared everywhere. It is not going to be shared also. Anything else? If no doubt nothing is there, then I will close it so that you can move to the next class or next lab. Suppose if you don't have any mic facility, if you want, you can type it in chat boxes also. No issue. So I'll be. For those who, if you feel it is clear, everything is clear, then you can leave the meeting. No issue.
సార్ అటెండెన్స్ అది నోట్ మీరు పెట్టారు కదా, మెయిల్ పెట్టారు కదా లింక్. సార్ మీరు అటెండెన్స్ లింక్ పెట్టారు కదా, అది నోటిఫికేషన్ లేట్గా వచ్చింది సార్ నాకు. అటెండెన్స్ ఉంది కదా
నోటిఫికేషన్,
క్లాస్ రూమ్ లో లింక్ పెట్టారు కదా సార్.
కొంచెం గట్టి మాట్లాడమ్మా, నువ్వు మాట్లాడే వినపట్ల. పృథ్వీరాజేనా?
ఎస్ సార్. సార్ లింక్ పెట్టారు కదా సార్ అటెండెన్స్ ది క్లాస్ రూమ్ లో, అది నోటిఫికేషన్ లేట్గా వచ్చింది సార్ నాకు. అది ఇప్పుడు
నోటిఫికేషన్ లేట్గా వచ్చింది. ఎన్నింటికి వచ్చింది
సార్? ఇప్పుడు 15 minutes.
ఎన్నింటికి వచ్చిందండి?
మినిట్స్ బ్యాక్ వచ్చింది సార్. 15 minutes బ్యాక్ వచ్చింది సార్ నాకు.
నేనేం చేయగలను? మీ ఒకటే సపరేట్ పెట్టాలి, నేను అందరికి ఒకేసారి పెట్టాలి. మీ ఒకటే లేట్గా వచ్చిందంటే మరి దట్ ఈస్ నాట్
నోటిఫికేషన్ పాప్ అవ్వలేదు సార్. బై
ఐ కాంట్ డూ ఎనీథింగ్ విత్ దట్ ఆల్సో. అందరికి ఒకేసారి పెట్టే, నేను మీ ఒకరికి సపరేట్ కాదు కదా, అందరికి గూగుల్ క్లాస్ రూమ్ లో పెట్టా. మీకు లేట్ ఎందుకు వచ్చిందంటే, బట్ ఐ డోంట్ నో ద రీజన్ వై యూ గాట్ ఇట్ లేట్.
నేను ఇప్పుడు అయితే పెట్టాను కదా లేట్ పర్మిషన్, ఎస్ అని పెట్టాను సార్. లేట్ పర్మిషన్ అని వచ్చింది.
No problem. So you responded for that. It's okay, huh? So I'll take that one as attendance, whether you are late. So but common in if you look at that one, so that means you attended the class late also. So it will reflect like that. Only that is the thing. Okay. Otherwise there is no attendance. But why it is put only particular time? Because people are joining at, see now even at the end of the class also some people are joining, so they will at our own leisure they are joining. So if the class is 9:15, 9:15, 9:16, 9:20, 9:30, 9:45, 10:15 వరకు జాయిన్ అవుతానే ఉన్నారు కదా. సో దట్ వై ఐ పుట్టెడ్ సమ్ రిస్ట్రిక్షన్ ఆన్ ద టైం షెడ్యూల్. సో లేట్ జాయిన్ అయ్యావా లేకపోతే టైంకి జాయిన్ అయ్యావా అనేది డజంట్ మ్యాటర్. జాయిన్ అయినాక వన్స్ నువ్వు ఫీడ్బ్యాక్ ఇచ్చావంటే ఇట్ ఈస్ టేకెన్ యాజ్ యు ఆర్ అటెండెడ్ ద క్లాస్. దట్స్ ఇట్.
9:14 కి జాయిన్ అయ్యాను సార్.
డోంట్ వరీ అబౌట్ దట్. లేట్గా వస్తే లేట్ వస్తుంది అంతే. బట్ నీకు అటెండెన్స్ అయితే అటెండెన్స్ వైజ్ ఇట్ ఈస్ నాట్ గోయింగ్ టు క్రియేట్ ఎనీ ప్రాబ్లం.
ఓకే సార్. ఓకే సార్. థ్యాంక్ యూ సార్.
Okay, right. So I think I am not seeing any question or any clarification needed in the chat box also. I am closing the class.